dear students, I'm Meghamala, Working Assistant Professor from Electronics and Communication Department, Institute of Aeronautical Engineering. And today I'm going to talk about a few problems based on the switch level modeling. Okay, so we will see how to solve problems when, in terms of switch level modeling. So we know that switch level modeling is one of the modeling styles in Verilog. So here we will see different examples, or else we will consider few examples based on the switch level modeling. So we know that switch level modeling is nothing but it is a level of modeling. It is a fourth level of abstraction in the Verilog, where we see how based on the switches. Okay, based on the switches, how the output is going to be considered, or else how the output is going to be enabled based on the switches. So basically in this switch level modeling, when we are discussing about the module 4, okay, module 4 switch level modeling, we have discussed about different switches, bidirectional switches, resistive switches, okay, and the basic switches. So now we will see the NMOS and PMOS switches. So these NMOS and PMOS switches are the basic switches in the switch level modeling. So in the code, when you are writing some code based on the switch level modeling, remember that the keywords, okay, if your module is in terms of, if your transistor or if your switch is in PMOS switch, then your keyword must be PMOS, right? So if your switch is in NMOS, and then your keyword should be NMOS, right? So here, to instantiate each element, okay, to instantiate each switch elements, switch name of the switch name, and here we have the instance name, okay, instance name followed with the port list. So how to write in the switch level modeling? When you're writing some code pertaining to the switch level modeling, so this is a syntax where you need to follow. It is switch name, the name of the switch, module comes first, the keyword, then goes with the switch name, and the instance name followed with the port list. So that port list consists of the input, output, and as well as the control signals. So based on the control signals, we can able to the output is to be enabled or disabled is calculated only with respect to the control signal. So here, if you see that this is a NMOS switch and this is a PMOS switch. So only difference between these two switches is here is for PMOS switch you can see a small bubble, okay, a small node or bubble. So here you have input, output, and as well as the control. And for NMOS, PMOS as well, you have input, output, and as well as the control. And now this is a truth table based on the control signals and the input lines. So here I can say that I have 0, 1, X and Z. You know 0 and 1 are the basic, what are these? The basics, the basic parameters, or the binary contains with respect to 0 and 1, right? And we have the X and Z. X is nothing but the Z is a high impedance value and X is a don't care condition, right? So here for NMOS, if my input is 0, what happens is the control line, if control line is 0, if control line is 1, okay, if control line is 1, what happens is my output as observed as 0, and X and Z values will becomes low, and 0 conditions becomes the high impedance value. So like that, when my control input, or else when my input is observed as 1, okay, when my input is observed as 1, what happens is the both X and Z values go with the high values, okay, high, and 0 goes with the Z. Likewise, this is a NMOS, and if you observe the PMOS also, it says the same thing, but the difference here we can observe is when my control signals are 0 and 1. When it is 0 and 1, what happens is the output goes with the 0 with respect to 0 and 1 with respect to 1. Okay, so that means what? There is a difference that you can observe in the NMOS and as well as the PMOS switches. So here the example, a small example given based on the CMOS inverter. So this is a CMOS inverter. We have the PMOS and the NMOS switch. Okay, they are connected to, both are connected to the input X, and output is observed as F is equals to X bar, and VDD is a power supply and it's grounded. This is a P and it is a N. So this is a basic circuit of a CMOS inverter. And now we will see this is a logic symbol. Okay, this is a logic symbol as it is a CMOS inverter is a logic symbol. If it is X, it is X bar. That is, if it is 0, it is 1. If it is 1 and it is 0. So this is a basic CMOS inverter, and in the switch level modeling, how the program can be written. This is what we are observing now. And now module is a keyword. Okay, name of the circuit, module is a keyword. Name of the circuit is my, not, or else CMOS. Simply you can write the name of a particular name of the circuit that you are considering. CMOS inverter, module, CMOS inverter. And in the port list, you need to mention the input and as well as the output. So the input is X and the output is F, right? So after that, internal declaration. So here, this is all about the internal. Internally, we are declaring all the inputs, outputs, supply, and as well as the ground and so on. So supply 1 as ground VDD, supply 1 as power supply VDD, and supply 0 as ground. Okay, all the initializing of the inputs and outputs are done. Then NOT gate body. Okay, now we will write the NOT gate body with respect to the PMOS. See, here we have the PMOS switch, right? So PMOS is a PMOS, all small letters. So the all small case. So this is a keyword. See, we are considering the PMOS switch, right? So our keyword should goes like PMOS. And if it is a NMOS switch, our keyword should goes like NMOS. So PMOS, P1. So for this PMOS, output is F, VDD, output is F, VDD and X. And then for NMOS, we have the F ground, right? For N, ground is connected, right? So F, ground and X. Then finally, N module. So this is how we can write a basic code with respect to the CMOS inverter. So in the exam point of view, if you're asked to write any code with respect to any kind of switches, then simply you need to remember, first draw the circuit diagram. In the circuit diagram, mention all the elements, all the inputs, outputs, power supply, ground, all the connections properly, and then draw the logic symbol as well. So after writing, you just write the mechanism. Okay, you just write the mechanism in the given code. So before you write the mechanism, you should start your code by writing the keyword, basic keyword module. In the port list, you need to mention all the input and output ports, all the initializing of inputs and outputs as well. And then finally, you represent, or else you need to write the mechanism of each and every switch interconnected to each other. Okay, so this is a basic example for CMOS inverter, and we will see one more example, that is CMOS NAND gate. So this is one of the example under switch level modeling, CMOS NAND gate. So this is a circuit. So here we see we have two PMOS and we have two NMOS, right? We have two PMOS and we have two NMOS. So here module, name of a module. So this is a CMOS NAND gate. Instead of my NAND, you can write CMOS NAND gate, right? CMOS NAND, any sort of name you can give. It's your wish. So module, CMOS NAND gate, and in the port list. So in the port list, I'm mentioning my inputs. Inputs are X and Y, and output is F is equals to XY. See, the name is CMOS NAND gate, right? NAND gate means AND plus NOT. AND plus NOT is nothing but NAND. So here, for this reason, for this circuit, I need to consider two PMOS and two NMOS, and they are connected serially, right? So then, finally, in the module, I am representing all my supply and for power supply VDD and as well as the ground. Then NAND gate body. So this is a NAND gate, right? So this is a gate structure, and this structure I am going to describe. Okay, so now I am going to describe with respect to the switches that I am considering. So here I have considered two PMOS, right? So for PMOS 1, whatever the elements are connected, the VDD is connected, F is the output, obviously we have, and X is the input. And similarly for PMOS 2, so for P switch, one more switch, VDD is connected, F is the output and X is the input. So similarly, I'm done with the P switch. Then immediately you have to write with respect to the NMOS switch. So for this NMOS switch, whatever the things are connected, it's connected with F, connected with X, and connected with A, right? And then for N2, connected with ground, connected with Y input, and connected with A. Okay, so this is how I'm going to write my code in terms of like all the by considering the what we say keywords, by considering the keyword pertaining to the P switch and pertaining to the N switch as well. And then finally N module. So this is a basic NAND gate. So here the output how I'm going to observe is, see, we all know AND gate, right? For 0, 0, 0, 1, 1, 0 and 1, 1. AND gate goes like the 0, 0, 0 and 1. And not gate is not for this is 0, 0, 0, 0. For if it is 0, it should be 1. And if it is 1, it should be 0, right? So AND plus 0, 1, 1. So this is obviously NAND gate, right? So 1, 0, 0, 0 and 1 finally. We will be 1, 1, 1 and finally we will be getting the output as 0. So X and Y to the NAND. Negation of X and Y is nothing but the NAND gate. So why we are considering this CMOS NAND gate means, we know that CMOS, which is complex metal oxide semiconductor, right? So CMOS NAND gate is how we can write the code in terms of by using all the keywords. And now we will see one more example as NMOS NOR gate. So we are concentrating on the NMOS. So for NMOS, only N switches are considered. So for this N switches, I'm saying that module, not NOR gate, input X, Y and output F, and then supply is 0. Okay, supply is 0, ground is 0. And see here, try one F to pull up the F node. So to pull up the F node, what are we considering is tri-state buffer, that is F, try one F. So these are nothing but the resistive switches. So this is a resistive switch. So in the resistive switch, I can consider the, if I'm considering my switch in terms of resistive switch, NMOS, if the NMOS is in resistive switch, I can write R NMOS, right? R PMOS, like that. Then NMOS is NX, N into X, that is F input, ground as well, and then X as the input. And for NMOS Y. So for this, with respect to Y, how can I write F as the output, ground as the input, and Y as the input. Y as the input, ground is the supply which is connected to the NMOS, and F as the output. And finally, I'm ending up with this end module. So these are the basic way of how to write the code in terms of switches with respect to different gates, NAND gates, NOR gates, and also with respect to the switches that you are considering. Sometimes I can consider my NAND and NOR gates with respect to the P switch, and sometimes I can consider NAND and NOR gates with respect to the NMOS switch. Then coming to the CMOS switch. So what is the CMOS switch? CMOS is nothing but it is designed to propagate both 0 and 1 as well. We know that CMOS is semiconductor metal oxide, so complex metal oxide semiconductor device, right? It's a switch. So it is designed in such a way that we can observe the output in terms of both 0 and 1 as well. And now NMOS is only able to propagate 0 and PMOS is only propagate 1. So NMOS is only able to propagate the 0 and PMOS is only able to propagate as 0. It propagates 0 and it propagates 1. Then to instantiate CMOS switches. So first is to design or else to propagate the output. We can propagate the output in two terms. One is with respect to 0 and 1, that is for NMOS 0 and PMOS 1, and to instantiate the CMOS switches. So to instantiate CMOS switches, how can we instantiate is CMOS, name of a, it's a keyword, it is pertaining to the CMOS switch, right? So keyword CMOS and their instance name, the name of the gate that you are considering, and the port list. So in the port list, we need to mention the input, output port, and as well as the control. If you are considering this CMOS switch consists of what? N and as well as P and as well as N, right? So if it is P and N, how many control signals that we can have is P control and N control lines, right? So here in the port list, I'm mentioning my output along with the data with P and N control signals. And after instantiating, we will instantiate the instance names. This instance name is optional. That means what? We can give the name or else we cannot give the name. That doesn't matter. So the instance name is optional, exactly equivalent to the following. So how it is optional is, see here we can simply write name of a keyword. See, this is the N switch, right? NMOS switch. So for this NMOS switch, I'm using a keyword called NMOS, and in the port list I'm writing out, data and N control. Okay, so here nowhere you can see the instance name. I said that it is an optional. It is an option. The name of that particular gate mentioning is optional. So there's need not to mention. So NMOS out data control, PMOS out data control. So this is a basic CMOS switch where you have P control, N control lines with data and as well as with the output. And now we will see an example in the switch level modeling, that is 2x1 multiplexer by using the switches. So here this 2x1 multiplexer is constructed with respect to the switches. So here we see the two CMOS switch. With the help of two CMOS switch, we have constructed this 2x1 multiplexer. So here module, name of a circuit, that is instance name, whether you can give or not, it doesn't matter. So name of a circuit, in the port list you are mentioning the input and output as well. And then output ports as out and input ports as I0, I1 and S. Why S is like we are discussing about 2x1 multiplexer example. In the 2x1 multiplexer we have selection lines, right? So selection lines are mentioned with S. I0 and I1 are the inputs and outputs are out. And then finally internal wiring. So for the connection purpose, the physical connection should be made with respect to the switches that we are considering. So the physical connections will be made with respect to the connecting wire. Wire is S bar, okay, wire S bar, and for not for the selection lines, not S bar and S. Okay, for this not S bar and S. This is S and this is S bar and S. And then for CMOS switches, and now coming to the switches, instantiation of the switches is done with respect to the CMOS. So for CMOS, CMOS, this is input 0 and output as observed as input 0 with respect to selection lines and S bar, and CMOS out. So for CMOS, input 1 with respect to S. So here you can take S and here it goes S bar. Okay, so CMOS out with respect to input I1 S bar, and for this 0 I0 S bar and out. Okay, this is how we will instantiate or represent the inputs and outputs with respect to the both inputs and along with the selection lines. And finally we are terminating the code with respect to the end module keyword. So this is a small example based on 2x1 multiplexer. And now we will see one more example, that is a CMOS flip-flop. So CMOS flip-flop, we know that flip-flop is a 1 bit of storage devices. Most of the registers, all the registers are nothing but the group of flip-flops are considered to be as a register. So now we will see the CMOS flip-flop. How is the module, name of a circuit is the module that we have considered is a flip-flop, C flip-flop, and the flip-flop consists of Q bar, D and clock. And then output representation or instantiating the input and output, specifically output Q bar, input D and clock. And then the connections, the nets. Okay, the net or the physical connecting that we are considering between all this is via E clock. Okay, these are the data types we can say. So internal nets via E and N clock, and then the clock inverter. So here we have the clock inverter by considering the clock and N clock. Okay, clock and N clock, and now goes with the switches. So we have constructed this flip-flop by using the CMOS switches. So for these switches, we know that the CMOS has the switch C1 is enclosed with the CMOS with E, D, clock and N clock as 1 when the clock is 1, and then the CMOS has E, Q, N clock and clock. This switch is all about the second switch, that is switch 2, when the clock is 0. Okay, when the clock is 0, the switch 2 will enable, and when the clock is 1, the switch 1 will be enabled. And finally instantiating the inverter as Q bar, okay, Q bar and E. And then finally NOT gate, Q bar is instantiating with respect to the NOT gate switch. So NOT of Q bar and N module. So this is a representation. See, you can see that here we have clock 1 and clock 1. And these two are the flip-flops, flip-flop 1 and flip-flop 2. This Q and Q bar and Q are the outputs. Okay, Q bar and Q are the outputs, and here we have a NOT gate. Okay, NOT gate is with respect to Q bar and with respect to Q, and then we have a one input as D and Q bar as the outputs. And then we know that the flip-flop has D as an input, Q bar as the output, and each and every flip-flops are associated with the clock signal. Okay, based on the clock signal, the transfer of information or else the enabling of the output will be happen. Then Q is the output and clock is the signal. And then, so this is nothing but the CMOS flip-flop. Okay. And then finally, in the out of 3 examples, if you observe in the switch level modeling, say so far we have discussed about different examples. One thing is 2x1 multiplexer. We have discussed example based on the CMOS NAND gate, and we have discussed about the NMOS NOR gate, right? NMOS NOR gate and CMOS flip-flop. So out of these all 4 examples, one thing we have remembered that in the coding, okay, when you're writing the code, always remember that the name of a circuit or module, the keyword should be given, and after that instance name. Instance name is an optional. Okay, there's we can give, we may not give. That doesn't matter at all. And after that, port list. So in the port list, always remember that in the switches you have the control signals, control lines. Right? So if you're considering the PMOS switch, then the control line should be P control. And if you're considering the NMOS switch, and the control line goes with N control. So based on the control lines, the output is on or off. That is what we can observe. That means what? In the PMOS transistor, when the control signal, when the control line is 0, okay, when the control line is 0, what happens is, when the control line is 0, the PMOS switch goes on. Okay, when the PMOS is on, NMOS will be off state. And when the control signal is 1, what happens is PMOS is 0 and NMOS, the N switch becomes 1. So this is a mechanism where we observe when it comes to the CMOS switches. So the CMOS switches is the combination of both PMOS and NMOS, and the examples that you are considering pertaining to the CMOS NAND gate or CMOS OR gate or the flip-flop, whatever you are considering, make sure that in the coding part, you have to write the module, name of a module, port list, and then go instantiation of input output, and then finally goes with the clock and as well as the inverters. Okay, inverters, clocks as well. And then finally remember that not to terminate your the code with the end module. This is very important. Module you have started and you have ended up with the end module. And also for all in order to connect all the elements, okay, all the gates or all the flip-flops, make sure that the physical connections is needed and you are representing it with a different nets called a wire. Okay, so this is a few examples based on the switch level modeling. I hope you all get it. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.